Hi guys, so today we're going to talk about section 6.2. All right, something I want to recap is the law of large numbers that we had back in chapter 5. And the law of large numbers states that as your number of trials increases, then your experimental probability of an event tends to approach your theoretical probability. All right, which we've gone over and over and over, where like if you flip a coin 2 times, it might be heads. But if you flip a coin 1,000,000 times, it's going to be 0.50001 probability of it being heads. The more trials you run, then the closer your probability gets. And then today what we're going to talk about models, like scenarios that model different combinations of bringing together different variables. Okay, so the first thing I want you to note is that none of this is on your formula card. Okay, this is more about a process that you need to understand than it is about like memorizing. Don't worry about memorizing all these symbols. We really just need to talk and think about the scenarios. Okay, so if you're talking about averages, if you have x as a random variable, so you have one variable, and then you're going to manipulate it with either multiplying that variable by an amount or adding amount to it, then you can just, the mean of your new transformation is going to be just put the mean into that transformation. And I'm going to explain it as I go through. Okay. If you have 2 variables, let's say men and women, the average height for men and the average height for women, and we want to find the average height of men plus women, like picture us stacked on top like heads, you know what I mean, like tall, like 12 feet tall, right? 11 feet tall, stacked that way vertically. You could just add together the average of men plus the average of women. If you're subtracting men minus women, it would be the average of men minus the average of women. If we want to find the average difference in our heights, we could just subtract the 2 averages. All right. For variances, here's the big deal. If it's see how this is a plus bx, like it was a plus bx up here? Up here, you also added the plus a. For a variance, you don't add the plus a. You're just working with whatever is the multiplier. Okay, so whatever kind of note you want to make, and of course, I'm going to give you examples in a few. All right, but you don't have the plus a. And then here, if you have the x plus y or x minus y, like I just talked about with this example, you add no matter what. Even if it's subtracting 2 variables, to get their variances, you add their variances. So you always add the variances and then square root the answer to get the standard deviation. So if a problem asks you for a standard deviation, you have to square them to get variances, add them together, and then square root that answer to get your standard deviation. It's not mathematically the same as adding together the 2 standard deviations. So, example 1. One brand of baby bathtub comes with a dial to set the water temperature. When the baby safe setting is selected, because babies you can't have the water too hot for babies. It's very bad for them. And the tub is filled. The temperature X of the water in a randomly selected bathtub follows a normal distribution with a mean of 34 and a standard deviation of 2. We want to let the water temperature in degrees Fahrenheit for the randomly selected bath, right? So y is going to be our Fahrenheit. So we've got here our y is equal to 9/5 C plus 32. We want to calculate the mean temperature in Fahrenheit. They gave us Celsius. All right, we want to find Fahrenheit. So the mean in Celsius is 34. The standard deviation in Celsius is 2. I want to switch it over to y's. So if we want the mean of y, we're going to do, take the mean of c. So y is 9/5 C plus 32. So we're going to do 9/5 times the mean of c plus 32 to get our Fahrenheit average. Okay, we're literally just plugging it in. So when you plug in 34 here, 9/5 times 34 plus 32 is going to give us 93.2 degrees Fahrenheit. That's the temperature. All right. Now, oh, and this should say and, not add. Calculate and interpret the standard deviation of y. For the standard deviation, this is what I was talking about before, where the mean, it was a plus bx. But for the standard deviation, you just use the b. Now, for a variance, you can square them both. For the standard deviation, you could just do b times sigma x. All right? You don't have to square them because the variance is the squares. This is just, so for this one, just the multiplier, you could use that. So your standard deviation of y, we're just using the multiplier. Okay, just the 9/5. We're not using the plus 32. So 9/5 times 2 will give us 3.6 degrees Fahrenheit. That's our standard deviation. If we interpret it, all right, then it will be the average distance from the mean, okay? Because that's our interpretation of the standard deviation. So that was one where it was in the a plus bx format. Let's look at one that's in a different scenario. So pause the video, read through example 2, and then come back to me, all right? If we want to describe the distribution of D, right, large minus C was your cup, right? The diameter, which one was it? Oh my goodness, I told you to read it. L was large and C represented what? A standard cup, okay? With this, or is L the lid? L is the lid and C is the cup. My bad, guys, sorry. So if we want to describe the center, right, if you're describing the distribution of D being the subtraction of the two, the lid's diameter minus the cup's diameter, we're going to find the average, all right, because center we can use average or median. It's going to be L minus D, so it's mu L minus mu C, sorry, not D. And we would get 3.98 minus 3.96, and we would get 0.02 inch. That's our average. Okay, that's our center. The shape is normal because we were told that up here, normal distribution, okay? The spread is your standard deviation. It's how spread out your data is. So it's how spread out you are from the mean. It's your standard deviation. This is where we're going to do the variance of the lid plus the variance of the cup. Even though the problem is L minus C, we always add our variances together. Okay, so we're going to get 0.02 squared plus 0.01 squared. And when we throw square root of that, and when we throw that in our calculator, I got these numbers from the problem, we're going to get 0.0224 inch. Right, and that's our standard deviation of L minus C. All right, this is mu D. You could have also written the standard deviation of D, okay, because that is L minus C. Now, for a lid to fit on the cup, the value of L has to be bigger than the value of C, but not by more than 0.06 inch. Find the probability that a randomly selected lid will fit on a randomly selected cup, and then we want to interpret this value. All right? So here's the key. The problem told us it's a normal distribution. So if the problem tells us it's a normal distribution and it's asking us to find a probability about this, then that's asking us to find the area under the curve. Okay, this is a normal curve. What goes at the center of our normal curve every time? All right, in order for it to be at the center, that's our mean. Our mean, we just found in part A, it's 0.02. All right, we're looking for L has to be bigger than C, but not by more than 0.06. So that means that L minus C has to be somewhere between 0 minus 0.06. Or you could look at it as D has to be somewhere between 0 and 0.06. So 0 is to the left and 0.06 is to the right of our mean 0.02. This is what I'm looking for. And it's been a while since we've worked with norm CDF, okay? But I'm going to use norm CDF to find the area under this curve. I could also use the z-score formula twice. Find the z-score for here, find the z-score for here, look them up, subtract your areas, come back, do that. But instead, I'm going to do norm CDF. It goes lower bound, upper bound, right? Where your shading starts, where your shading stops. The mean is 0.02 and the standard deviation is 0.0224 that I found up there. Okay, this probability is 0.7770. So that's our probability of being between those two values. If we interpret it, that means there's a 77.7% chance that the cup fits, the lid fits on the cup. Okay, that it's not going to be too big and it's not going to be too small. That it fits just perfectly. That's actually pretty terrible. That would be a lot of cups wasted, a lot of lids wasted, but that's okay. All right, let's do another one. Okay, number 3. In a large introductory stats class, the distribution of x equals raw scores on a test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to, so if you want, you jot down the mean of x is 17.2, the standard deviation of x was 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. So we want to define y to be the scaled score. So what are we going to do? We're going to let y equal, multiply the raw scores by 4 and add 10. So it's 4 times x plus 10, right? Because x is your raw score. So y is your scaled score. Now we want to find the mean of y. This is like that a plus bx format that I showed you on the previous page. So your mean of y is just going to be 4 times the mean of x plus 10. You can just plug your mean in. So 4 times 17.2 plus 10 should give us the mean of y. The mean of the scaled score is 78.8. Okay, your standard deviation of y, think back, what happens? We don't use the plus 10. It's just 4 times your standard deviation of x. So it's just 4 times 3.8, and we get 15.2. That's our standard deviation of y. Okay. What's the probability that a randomly selected student has a scaled score of at least 90? Well, we were told in the problem that they're normally distributed. So we can jump on over to our normal curve, right? What goes in the middle? The mean. The mean is 78.8. We want a score of at least 90, so we're going to have 90 and above we're going to have here, okay? So norm CDF, lower bound 90, upper bound infinity because the shading stops at infinity. We have a mean of 78.8, standard deviation of 15.2. Remember, lower bound, upper bound, mean, standard deviation. You cannot just write calculator talk without identifying what you're working with. When you put that in your calculator, you get 0.2306, and that should be your answer. All right, so let's do another. Rotter Partners is planning an investment, a major investment. From experience, the amount of profit X in millions of dollars on a randomly selected investment of this type is uncertain. But here's an estimate that gives in a probability distribution. Based on this estimate from section 5.1, they already found the mean for you and the standard deviation. Remember how we multiply, like do this plus, multiply this plus, multiply this plus. That's your mean. Okay, so they figured out the mean and the standard deviation for us. They owe their lender a fee of $200,000 plus 10% of the profits X. So that means that the firm is retaining or keeping 0.9x, right? If you pay 10%, that means you keep 90%. And if it's a fee of $200,000, that's 0.2 of $1 million because it's giving us profit X in millions of dollars. So they're retaining Y equals that. We want to find the mean and the standard deviation of Y. So we have the mean of Y is going to be 0.9 times the mean of x minus 0.2. Right? If y equals 0.9x minus 2, then we're going to plug in the mean of x here. So the mean of x is what? 3 minus 0.2. So the mean of y is 2.5, and it's $1 million. Okay, that's what they can expect. For your standard deviation of y, it's 0.9 times the standard deviation of x. And our standard deviation of x is 2.52. So our standard deviation of y is $2.268 million. All right, guys, so your job is to try this problem on your own. Okay, give it a shot. This is one of my all-time favorite problems from AP Stats. I think it's such a neat, cool problem. I love it. So try this in pencil or on a separate sheet of paper, and then I know you're going to remind me this is how we're going to start our next class. We're going to go over this, okay, when we're together. Good job today.